My name is Keshav, and I'm a rising senior in the Bay Area. Over the past few months, I've worked with my mentor Sarah to write a research paper called Responsible AI for Nonprofits, Ensuring Data Privacy and Mitigating Bias in Large Language Models. Over the last 3 years, I've worked with three nonprofits across industries. Clarkin Street Youth Services and Youth Spirit Artworks are shelters for unhoused youth in Oakland and San Francisco. And Everything ALS is an organization working to find a cure for the neurodegenerative disease ALS. I've noticed a common fear of using AI due to concerns such as data privacy and bias, and a worry that AI will replace human jobs. This inspired me to conduct research to tackle these concerns and develop a comprehensive guide to empower nonprofits to use AI safely and effectively. Large language models are revolutionizing our world with their ability to understand, generate, and manipulate human language based on vast data sets. LLMs have immense potential for nonprofits to enhance fundraising, community engagement, and program effectiveness. But compared to an industry standard of 70%, only around 30% of nonprofits use AI, as safety is especially important for their communities. It is essential that personal information and training data is not leaked, and that the model is not influenced by inherent biases. This led me to propose the following three research questions. Number one, what are the risks associated with data privacy in LLMs, and how can we go about addressing them? Two, how do we define bias in AI, and what steps can we take towards measuring and mitigating bias? And three, what are the primary use cases and limitations of using AI at nonprofits, and how can we use this knowledge to create a set of guidelines for responsible and effective AI use? Our thesis states that in this paper, we propose strategies to combat data privacy and bias and issues in LLMs, applying this research to create a guide for nonprofits to use AI safely and effectively. There are a number of concerns associated with data privacy in LLMs, most notably leakage of sensitive personally identifiable information, or PII. As LLM outputs are based on the data used to train them, pre-trained models such as ChatGPT can retain or memorize personal data and return them in outputs when presented with the right context. When PII is leaked, a person's personal identifiable information may be used against them. We refer to this as an objective privacy harm. Subjective privacy harms, on the other hand, do not require PII and give someone the feeling as if they're being watched over. PII can either be leaked through random prompting of LLMs or attacks with malicious intent that exploit AI inherent vulnerabilities. These issues have been brought about in several legal concerns regarding user consent, data processing, and copyrighted information. Synthetic data is the most simple solution to data privacy, involving replacing PII with placeholders or fake information. One drawback to synthetic data, however, is that using artificial data may cause the model to lose effectiveness, as it no longer has the same context as before. The data privacy vault depicted in the figure stores PII in a secure vault so that it is not used throughout the AI pipeline, but can still be safely accessed by authorized individuals. Differential privacy adds noise to model outputs during computation, allowing the final result to differ slightly from the base model, removing specific details such as PII. As shown in the figure, given two datasets that only differ by a single entry, Joe's data in the figure, their results should never differ by more than a certain amount. This ensures that specific data points, including PII, are not overemphasized in the generation process. Differentially private stochastic gradient descent, DPSGD, and private aggregation of teachers' ensembles, PATE, are two differential privacy algorithms. DPSGD adds noise to prevent the model from learning too much from a certain data point, but with PATE, multiple teacher models are trained on different datasets to vote and classify new model inputs and ensure that specific data is not used to make the overall prediction. Homomorphic encryption is a method that enables computational operations on encrypted data, allowing PII to remain safe throughout the machine learning pipeline. Secure multi-party computation is a subfield that facilitates computation from multiple encrypted data sources. Each party shares a random portion of its data with the other parties involved, so that the combined dataset includes data from all the parties, without leaking specific information to the other parties. Now let's shift our focus to bias. In the context of LLMs, bias occurs when the model's outputs unintentionally reflect social prejudices. The potential harms of bias in LLMs are significant. They can perpetuate stereotypes, lead to discriminatory practices, and worsen existing social inequalities. As depicted in the figure on the right, although statistical and computational biases amplify prejudice, Bias in AI stems from human and systemic biases in the underlying data used to train AI. Our paper classifies types of bias into several categories, including representation and favoritism biases, where a particular group or idea is favored or overrepresented, such as a particular race or gender, and prominence and trend biases, where certain portions of the dataset are favored, such as information from authorities and current events. We propose a three-step architecture for mitigating bias in LLMs that begins with defining bias and fairness. Bias and fairness are complex topics that manifest in a number of ways and oftentimes depend on the context or culture in which they are brought up. Each organization should take the time to craft their own definitions of bias and fairness by examining what is most important to achieve equitable decision-making for their specific use cases of LLMs. The next step is to apply fairness metrics to detect and monitor bias. Measuring bias depends on ensuring that protected attributes, such as race and gender, are not used in the decision-making process to prevent minority groups from being discriminated against. Our paper covers several types of fairness metrics that use the training data in the model outcomes to measure bias. The third and final step is reducing bias with bias mitigation algorithms. Bias mitigation algorithms occur in three different places in the ML pipeline: pre-processing to modify the training data, in processing while the model is being trained, and post-processing to modify the model outputs. Our paper dives further into the specifics of these mitigation algorithms. The Pareto frontier is a set of solutions that represents the best trade-off between all objectives. The paper, Learning to Walk Impartially on the Pareto Frontier of Fairness, Privacy, and Utility, proposes applying this concept to simultaneously optimize for data privacy, bias mitigation, and accuracy. The graph to the right depicts all possible solutions, measuring all three objectives. The solutions on the Pareto frontier are such that improving any one objective worsens another. The Pareto frontier paper proposes two algorithms, Fair DPSGD and Fair PATE, that combine differential privacy with fairness metrics, achieving stronger results than baseline models across objectives. We are just scratching the surface in terms of optimization in AI, and we identify fields like the Pareto frontier to be interesting and important research areas for the future. Our paper concludes with a guide for nonprofits to safely and effectively implement AI. It begins with information on how to implement the data privacy and bias mitigation techniques we discussed earlier. We recommend using synthetic data for smaller scale use cases and teams without technical backgrounds. We recommend differential privacy and homomorphic encryption approaches for more advanced applications with lots of backend data developed by teams with more stronger technical backgrounds. DPSGD is particularly useful for generation tasks, while PATE is great for classification tasks. Multi-party computation is a recommended approach for data collaboration between organizations. In terms of bias mitigation, we recommend that companies personalize their procedures to their own use cases and priorities using the metrics and mitigation algorithms proposed in our section on bias. The guide continues with other concerns and limitations with LLMs. Other concerns include unreliable outputs, high computation costs, and the fear that AI will replace human jobs. Limitations include a lack of personalization and domain-specific knowledge, alongside inherent issues such as lack of human emotion, intuition, and creativity. We then propose guidelines and standards for nonprofits to adopt. It begins with a list of safe use guidelines for AI, such as staying organized, training staff, vetting your vendors, and taking it slow at first. It also covers managing secure and unbiased data and staying human-centered, using AI to augment work instead of replacing it. We believe that nonprofits are in a unique position to promote open source information and transparency with AI, used to build trust in their community. We also cover legal compliance, highlighting user consent as the most important guideline. We conclude with applicable use cases of AI and LLMs at nonprofits. AI has the potential to revolutionize areas like fundraising, community inquiries, legal compliance, spreading awareness, personalization, volunteer management, donor retention, and report generation. My research has been super helpful in my work using AI at nonprofits, and I hope that it empowers all kinds of nonprofits to better understand AI and its ethical concerns and feel confident harnessing its potential for social good. Thanks so much for listening.